Welcome to one of the most revolutionary moments in physics history. Today we're going to explore the photoelectric effect, an experiment that completely shattered our understanding of light and forced us to create an entirely new branch of physics called quantum mechanics. Let's start with what physicists expected based on classical wave theory. According to classical physics in the late 1800s, light was understood as an electromagnetic wave, just like water waves or sound waves. If light is a wave, then the energy it carries should depend on the wave's intensity, which means how bright the light is. Think of ocean waves. Bigger, more intense waves carry more energy and can knock you over more forcefully. Here's a visualization. The top shows a low-intensity wave with small amplitude. The bottom shows a high-intensity wave with large amplitude. Classical physics predicted that more intense light should give electrons more energy. So the classical prediction was crystal clear. If you shine brighter light on a metal surface and knock out electrons, those electrons should come out with more kinetic energy. The brighter the light, the faster the electrons should move. Now let's design the actual experiment that tested this prediction. The setup is beautifully simple yet incredibly powerful. Here's the experimental setup. We have a metal plate on the left. We shine light of various intensities and colors onto this metal. When light hits the metal, electrons are ejected, and we can measure their kinetic energy using electrical circuits. We can measure two things very precisely. First, the kinetic energy of each individual electron that comes out. Second, the number of electrons ejected per second, which we call the current. Let's perform our first experiment. We'll use red light and vary its intensity from very dim to very bright, while carefully measuring the maximum kinetic energy of the ejected electrons. We start with very dim red light, then gradually increase the brightness to medium, then to very bright red light. Classical physics predicts the electron energy should increase linearly with intensity. Here are our three intensity levels visualized. Top is dim red light, middle is medium brightness, bottom is very bright red light. Each represents a different wave intensity hitting our metal surface. Before we look at the data, let's plot what classical physics predicted we should see. This is crucial because we need to compare prediction with reality. Here's the classical prediction graph. The horizontal axis is light intensity. The vertical axis is electron kinetic energy in electron volts. Classical physics predicted a straight line. Double the intensity, double the electron energy. Now comes the moment of truth. Let's perform the experiment and plot the real measured data points. What we're about to see contradicted everything physicists thought they knew about light. This is shocking. The green line is the classical prediction. But look at the red line and the yellow data points. The electron energy is completely flat. It doesn't matter if we use dim light or incredibly bright light. The maximum electron energy stays exactly the same at about 1.8 electron volts. Let me repeat this because it's so important. Whether we shine dim red light or blindingly bright red light, every single electron comes out with the same kinetic energy. This makes absolutely no sense according to classical wave theory. You might ask, if electron energy doesn't change with intensity, what does change? Great question. What changes is the number of electrons ejected per second. Brighter light ejects more electrons, but each electron has the same energy. Here's a visualization. On the left, dim light produces few electrons, shown as small red dots. On the right, bright light produces many more electrons. But crucially, each individual electron has exactly the same kinetic energy, regardless of which side it comes from. Physicists tried every possible classical model. They tried different wave equations, different energy transfer mechanisms, different time delays. Nothing worked. No classical wave theory could explain why electron energy is independent of light intensity. So if intensity doesn't change electron energy, what does? Let's perform a second experiment where we keep the intensity constant but change the color of the light from red to orange to yellow to green to blue to violet. This time we use the same brightness for all colors. We'll shine red light, then orange, then yellow, then green, then blue, then violet, all at the exact same intensity, and measure the maximum electron energy for each color. Here are our different colors of light, all at the same intensity, from left to right: red, orange, yellow, green, blue, and violet. Each color corresponds to a different frequency of electromagnetic radiation. Now let's plot the results. This time, our horizontal axis is the frequency of the light, which corresponds to its color. Red light has low frequency, violet has high frequency. This is absolutely stunning. The data points form a perfect straight line. The electron energy increases linearly with the frequency of the light. Red light with low frequency produces low energy electrons. Violet light with high frequency produces high energy electrons. This is the breakthrough insight. The energy of each ejected electron depends entirely on the color or frequency of the light, not on how bright the light is. This was completely unexpected and unexplainable by classical physics. The equation that fits this data perfectly is E electron equals hf minus W, where E is the electron's kinetic energy, F is the frequency of the light, H is a new constant called Planck's constant, and W is the work function of the metal. The slope of this line is Planck's constant, h, which equals 6.63 times 10 to the negative 34 jouleseconds. This tiny number became one of the most important constants in all of physics. Let's step back and understand why this was such a crisis. Classical wave theory said energy should depend on intensity. But the experiments showed energy depends on frequency instead. This contradiction could not be resolved within classical physics. Here's the key question physicists had to answer. Why should the color or frequency of light determine the energy of individual electrons? Frequency is just how fast the wave oscillates. In wave theory, that shouldn't affect the energy delivered to each electron. In 1905, Albert Einstein provided the explanation that would earn him the Nobel Prize. His idea was radical. Light is not just a wave. Light also behaves as if it's made of particles. Einstein proposed that light energy comes in discrete packets called photons. Each photon carries a specific amount of energy that depends only on the light's frequency. The energy of one photon is h times f. Here's a representation of photons. Instead of a continuous wave, light is actually made of individual packets of energy. Each yellow circle represents one photon carrying a specific quantum of energy. The energy of a single photon is hf, where h is Planck's constant and f is the frequency. High-frequency violet light has high-energy photons. Low-frequency red light has low-energy photons. Now the photoelectric effect makes perfect sense. When a photon hits an electron in the metal, it transfers all of its energy to that one electron. One photon knocks out one electron. The electron's energy equals the photon's energy minus the work needed to escape the metal. Brighter light just means more photons per second, but each photon still has the same energy determined by the frequency. So brighter light ejects more electrons, but each electron gets the same energy kick from its individual photon. Compare red light on the left with violet light on the right. Both have the same number of photons, so they eject the same number of electrons. But violet photons carry more energy each, so the electrons from violet light have higher kinetic energy. Let me give you an analogy that captures this beautifully. Imagine you're trying to knock cans off a shelf. The classical wave view is like using a water hose. You'd expect that increasing the water pressure, the intensity, would knock the cans off with more force. More water flow equals more energy transferred to each can. But the quantum view is different. It's like throwing individual balls at the cans. The number of balls you throw per second is like intensity. It determines how many cans fall. But the energy each can gets depends on how hard each individual ball is thrown, which is like the photon energy or frequency. If you throw many ping pong balls, you knock down many cans, but gently. If you throw fewer baseballs, you knock down fewer cans, but each one flies off with much more energy. The type of ball determines the energy, not how many you throw. There's one more crucial prediction of the photon model. If photon energy equals hf, then below a certain frequency, photons won't have enough energy to eject electrons at all, no matter how bright the light is. Look at this graph. The line intersects the horizontal axis at the threshold frequency, shown by the green dashed line. Below this frequency, even infinitely bright light cannot eject a single electron, because each photon lacks sufficient energy. This prediction was tested and verified. Shine incredibly bright red light on certain metals, and you get 0 electrons. But shine even very dim ultraviolet light, which has higher frequency, and electrons immediately start coming out. This proved light truly consists of photons. The photoelectric effect was one of the key experiments that forced physicists to abandon classical physics and develop quantum mechanics. It showed that energy at the microscopic level is quantized, coming in discrete packets rather than continuous amounts. Quantization means energy can only exist in specific discrete amounts, like how you can have 1, 2, or 3 photons, but not 2.5 photons. This was a completely new way of thinking about nature. Before quantum mechanics, physicists believed all physical quantities were continuous. Energy could have any value. But the photoelectric effect proved that at the atomic scale, energy is granular, existing only in specific quantized amounts. The photoelectric effect also demonstrated wave-particle duality. Light exhibits wave properties like interference and diffraction, but it also exhibits particle properties as shown by the photoelectric effect. Light is both wave and particle simultaneously. You might think this is just abstract physics, but the photoelectric effect is the basis for countless modern technologies that you use every single day. Solar panels work because of the photoelectric effect. Photons from sunlight hit semiconductor materials and eject electrons, creating electrical current. Without understanding quantum mechanics, we couldn't have developed efficient solar technology. Every digital camera and smartphone camera uses photoelectric sensors. Each pixel contains a photodetector that converts incoming photons into electrical signals, which are then processed into the images you see. Night vision technology uses photomultiplier tubes that amplify the small number of photoelectrons generated by dim light, allowing us to see in near darkness. Let me summarize the profound lessons from the photoelectric effect. Classical wave theory predicted that brighter light should produce higher energy electrons. This seemed completely logical based on how waves transfer energy, but careful experiments revealed that electron energy is completely independent of light intensity. Brighter light only produces more electrons, not more energetic electrons. The graph was flat when it should have been a rising line. The breakthrough came when physicists discovered that electron energy increases linearly with light frequency. Color, not brightness, determines the energy of each electron. Einstein explained this by proposing that light consists of photons, quantum particles of light. Each photon carries energy equal to Planck's constant times the frequency. The photoelectric effect was one of the key experiments that forced the development of quantum mechanics, fundamentally changing our understanding of nature and enabling modern technology. Remember this beautiful equation. The energy of a photon equals Planck's constant times frequency. This simple formula encodes the quantum nature of light and energy. The photoelectric effect teaches us a profound lesson about science. When careful experiments consistently contradict accepted theory, we must be willing to revolutionize our understanding, no matter how strange the new ideas may seem.